last video we have derived an equation that relates the built-in potential with the electron concentration at the surface at equilibrium. So let's write this down again. So we have we have stated that the built-in potential determines NSO. NSO was the concentration of electrons at the interface in the semiconductor when we are in equilibrium, meaning that no net charge is transferred across the phase border. So what was the equation? The equation was NSO is equal to NB times the exponential minus Q, the built-in potential over KT, the thermal energy. However, in the last video I said one can derive this by starting or by using the potential difference between the phase border here and the bulk. Yeah, it's true, but actually I thought about this a bit, and actually you can also derive it by using the electrochemical potentials, or can be derived with mu tilde of E, the electrochemical potential of the electron, or let's say with delta U E, delta denoting the difference between the phase border and the bulk. However, a good resource still is also the Wikipedia article about the chemical potential in the German Wikipedia. There this is explained in a quite good manner, I would say, if you're curious about it, or still ask, write an email or so, if you want to know further details. However, we have now derived an equation that, or not derived, but stated an equation that gives us the electron concentration at the surface, or at this interface here, at equilibrium. But we need also, or we can know, or we can think that the applied external potential, difference drives us away from equilibrium, drives us away from equilibrium. Meaning that if an external potential difference is applied across this border, or the phase border between the semiconductor and the electrolyte, what will change? So NS will change. We now have NS instead of NSO, the equilibrium surface electron concentration, and this is equal to, again, bulk, but an exponential term, minus Q, also again the built-in potential, plus with externally applied potential over KT. That's it. So now how are these two equations for NS and NSO, how are they going to help us in developing an equation that describes the charge transfer across this barrier? Yeah, it's not far away, because what did we have in the last lecture or the last video? we had an equation that is valid away from equilibrium. Away from equilibrium, it also holds that this guy here, the change of electron concentration in a semiconductor here, is not zero. And it is, what do we have? Plus the KET is just a constant. Then we had the surface electron concentration. Then we had the concentration of species A, this guy here that can accept electrons at the surface. So this term refers here to the probability that an electron leaves the semiconductor, and we have to subtract. Basically it's repetition of the last factor, minus 1, and minus s at the surface. So this term here refers to the probability that an electron is injected into the semiconductor. The more of this you have here, the more can go inside. And in the last video we have also developed an expression for the equilibrium condition, and we have plugged this condition for equilibrium into this equation and ended up with the following equation. It's just KET. Then I think it was AS, and it's MS minus NS at equilibrium, surface concentration at equilibrium. Yeah, it should be correct. And if we plug in these two guys here into this equation, then we end up with dN over dt is equal to, so the proportionality constant is still there, a S is still there, we can pull out NV, we can pull out the exponential term with built-in potential. This is now elementary charge, externally applied potential, KT minus 1. So now we are very close to what we want. This should already look quite familiar to you, or hopefully yes, because it's a diode equation. It's very similar. The only thing left to do here now to have relation between the current and an externally applied voltage is multiply with the negative charge, because we are interested in electron flow, negative elementary charge, and the surface area here, or the interfacial area here at this interface. So multiply with negative Q and A gives us an expression for the current, I0, so elementary charge, externally applied potential, minus 1. Okay. So again, let's repeat a bit. What do we see here? It's an equation describing the charge transfer across this here would be the electrolyte for completeness. And here we have the semiconductor. This is the phase border. And the current that is transferred independence of externally applied voltage is the diode equation, yes. How is this really justified? We have here I0. I0 contains all these terms here, so the built-in potential can be considered as a constant. The bulk semiconductor concentration is also constant AS in the first approximation can also be considered as a constant, and it can be considered as a constant as long as you have enough fresh supply of these A guys here, or let's say if you stir the solution, then it's good. I think also this approximation can be made. However, the approximation of this being a constant is lost when it's heavily consumed here and you already have a low concentration of A in the solution. But however, for our purposes, we will treat it as a constant. And KET, this proportionality constant, contains a lot of information that we will not cover here, but the theoreticians are very interested in it. For example, how exactly the mechanism is of the electron transfer between the electrolyte and the semiconductor, how this happens is incorporated into this KET guy here. So I will now clean the board. In the next video, I think it will be the last video on about the theory. I would like to talk about what happens when this is illuminated with light, and also maybe a bit more information about this equation here. So yeah, see you in the next video.